Okay, so in this example we have a little simple mechanism with rollers at each end, at points A and B namely, and we're told that VB is moving to the right with a given speed. And given this piece of information, in addition to the angles theta and phi, as well as the length of the rod, we're asked to determine the angular velocity of the link, the speed of end A, as well as the speed of point G, a point near the center of the link. Okay, so the way I want to do this is as follows. I'm going to start by trying to note that I know the direction of velocity at one point, namely point A, has got to be somewhere along this path, and I know also that the velocity of point B identically. And so given this information, I can draw in perpendicular construction lines, and if I do this, I will end up with the fact that the instantaneous center of link AB is somewhere down here like so. Now that piece of information may seem useful at first, and then you realize quite quickly that you actually need to find some additional distances here. And so the way I'm going to do this is a bit of a trick. I'm going to try to break this triangle up into two triangles, which are both right triangles. So I'm going to draw a horizontal line here through point A, and note that these are both right angles. And then if I do that, I quickly realize I have one triangle here, that is a right triangle, with hypotenuse length L, which means this little length segment right here has to be L times the cosine of the angle phi, and this little length right here has to be L times the sine of the angle phi. And in addition to that, I have a second triangle, which I will call right here, and I'll sketch it in green. And I'll note that this interior angle right here has to be the angle theta, which means that this length here has to be, if I call this length right here d times the cosine of theta, and this over here has to be d times the sine of the angle theta. Now why is that useful? Well, now I can actually start to compute some useful engineering quantities. Namely, I can start by saying that omega AB, the angular speed of the link, has to be the speed of point B divided by the distance between B and the instantaneous center at point AB. This is now relatively straightforward to compute because I know this is going to be VB divided by, in this case, L times the sine of the angle phi plus D times the sine of the angle theta. Now you might say, well, you don't have a clean relationship yet to compute D, but in actuality we do. Because these two triangles share this middle ground here, namely this line right here, I can say that I know L times the cosine of phi has to equal D times the cosine of theta. And so I can find D from this and simply say D then is L cos phi divided by cosine of theta. And with this information, omega AB comes completely known. I can also use that and say then I realize that omega AB has to be clockwise, which means that my vector version of omega AB, namely the angular velocity, has to be VB divided by L times the sine of phi plus D times the sine of theta in the k direction. Now if I use that information, I can also find the velocity of point A, namely the speed of point A has to in this case be D times omega AB, which in this case is simply going to be VB times D divided by L times the sine of phi plus D times the sine of theta. And if I want to write this in vector form, all I have to do is simply say then, well, the vector VA is going to be the same scalar, VB times D divided by L times the sine of the angle phi plus D times the sine of the angle theta times a unit vector along that path. And so in this case, I know it's going to be oriented along an angle-oriented theta, and so this is going to be the cosine of the angle theta in the I plus the sine of the angle theta in the j, presuming of course I use conventional I-j notation. Now with that piece of information in hand, I can also find the velocity of point G, if I want to do that. And in this case, perhaps what it would be easiest is to simply note that the velocity of point G is going to equal the velocity of point B plus the omega of the bar, AB, crossed with the position vector between G and B. And I'm going to choose to do this instead of simply using the method of instantaneous centers with this last part, because I don't want to have to do the mess to figure out the length of the line between point G and the instant center. So if I do this, I'll have the velocity of point B is simply going to be VB in the I. I've already found that omega AB is equal to VB divided by L times the sine of the angle phi plus D times the sine of the angle theta in the k. And I can cross-site with the position of G with respect to B. So if I go up to my diagram here, we know G's at the midpoint, the bar is oriented at an angle phi, and so in this case this is going to be minus L over 2 times, in this case, the cosine of the angle phi in the I, minus L over 2 times the sine of the angle phi in the J. And so if I go ahead and work out my cross product here, I'm going to have this is equal to VB in the I. K cross I is going to give me a J, so I'm going to have minus VB times L times the cosine of the angle phi divided by 2 times quantity L times the sine of the angle phi plus D times the sine of the angle theta in the J direction, and K cross J gives me minus I, so I'll have plus VB times L times the sine of the angle phi divided by 2 times quantity L times the sine of the angle phi plus D times the sine of the angle theta in the I direction. And that should just about wrap up this problem. From here you can just plug in numerical values and you'll be good to go. I know you can do it. Best of luck.